So in the previous session, Nisark discussed different notions of fairness that derive from economics and can be very nicely applied in different machine learning applications. So we discussed about unfairness already. And now in this part of the session, we will talk about non-social welfare and the core. And we will see the applications of these different notions in different settings like multi-embodied, classification, and clustering. All right, without further ado, let's start. So we have already seen the definition of non-social welfare, so I will just start by considering its application in a multi-embodied setting. So for those that are not familiar, what is a multi-embodied setting? So imagine that we have an agent and we have k different arms or k different slot machines from which an agent can choose. And the idea is that every time that we pull an arm, the agent observes a reward which is drawn from an underlying unknown distribution. And so the goal of the agent is to try to find the arm that is the best for her, which means the arm that maximizes her mean expected reward. So if she knew from the very beginning what was the best arm, what was the arm that maximizes her expected utility, then she would always play this arm. But the problem is that the underlying distributions are unknown. And so this multi-embodied framework captures the famous exploration versus exploitation dilemma, which means that in some rounds we should explore the different options that we have at hand, and in some rounds we want to exploit the knowledge that we have learned and try somehow to gain more reward. And so in general, the objective and the goal in this multi-embodied setting is to try to minimize the regret, which is defined over a time horizon capital T, which means that if the players can play up to capital T rounds, so you can imagine it has different coins and it has a total capital T coins, and so she wants to maximize her reward using these available coins. And so the regret is defined as what she could have gained if she knew from the very beginning what is the machine that has the highest expected reward minus what she loses by making suboptimal decisions in different rounds. So this is the classic multi-embodied setting. So in a recent work with Safhan, Hossein, and Nisark, we consider a variation of this classic problem, which we called multi-agent, multi-embodied setting, where here we assume that we don't have just one agent, but essentially we have n different agents. And so whenever we pull an arm, we don't see just one reward, but we see n different rewards for the n different agents. So you can imagine that for each arm and for each agent, there exists an underlying distribution. And whenever we pull an arm, we see n rewards that are drawn from the n different distributions underlying. So this model captures applications like non-personalized recommendation systems, for example, where we advertise a particular product to a bunch of different users, and now the users might have different utilities about this product. And so we want to take into account this heterogeneity and to find a policy that's fair with respect to all of them. And so the challenging here is that different people might have different utilities. And so now probably different people perceive a different arm as the best for them. So before, because we had just one agent, the goal was to try to find the best arm for this agent. But now probably the first user prefers the first arm, the second agent prefers the second arm, and so on. So there's no anymore the notion of the best arm. So even if we ignore for a while the fact that we don't know what are the underlying distributions, even if we knew everything, the challenge here, first of all, is to decide what is a fair policy. The first observation is that a policy in this case should not be just a deterministic arm, because if we just choose to play always a particular arm, then unavoidably we will be unfair with respect to some group of people. Because, for example, you can imagine that we have two agents and two arms. The first agent prefers the first arm, the second agent prefers the second arm. If we just always play the first arm, then unavoidably we will be quite unfair with respect to the second agent. And so that's why in this work, a policy that we want to find is not just picking one arm forever, but having a distribution over the different arms, and we want to ensure that this distribution is in some sense fair. And so when we have this distribution, the expected reward of an agent is defined as this expectation over the distribution that we have. So imagine now the scenario that we have 2 slot machines and we have 3 different agents. The first 2 agents, so the first machine is great for the first 2 agents because it always returns reward equal to 1, while it is not good for the third agent because it always returns reward equal to 0. And imagine that for the other slot machine, it is exactly the same, exactly the opposite case, which means that it is very bad for the first 2 agents, but very good for the last agent. So the question here is, what is a fair policy? So as Nisark mentioned in the first session of this tutorial, we can try to maximize different welfare functions that derive from economics. And one very famous is to try to maximize the utilitarian welfare, which means that we try to find the policy that maximizes the sum of the expected rewards of the different agents. But then in this particular example, if indeed we try to find the distribution that maximizes the utilitarian welfare, we see that the optimal distribution is to always pick the first term with probability 1 and never pick the second term. And this is not very surprising because we already know that utilitarian welfare has the drawback that causes the tyranny of majority, which means that whatever the majority prefers, this is what we are going to select. Now, another option is to try to maximize egalitarian welfare, which is try to maximize the minimum expected reward, maximize the minimum expected reward over all the agents. And in this particular instance, you can see that the policy that maximizes egalitarian welfare is the one that chooses the first term with half probability and also the second term with half probability. So this might be fairer than the first one in some cases, but still doesn't seem very fair in the sense that 2/3 of the people prefer the first slot machine and 1/3 of the population prefers the second machine, but still we select the 2 different machines with the same probability. So we want something more proportionally fair in this case. And this is exactly what NASA's rule of fair does in this particular example. So if we try to maximize the product of the different expected welfares of overall the agents, then we see that the policy that maximizes the natural welfare is the one that we pick the first machine with probability 2/3 and the second machine with probability 1/3. So essentially here we see that we achieve this proportionality by trying to maximizing non-social welfare. And so in this work, we decided that we will choose that the optimal policy is the one that tries to maximize the social welfare, but now how can we really take into account that the distributions are unknown and how can we really try to minimize the regret in this setting? So first, we define the regret as the optimal social welfare that we could achieve over all the rounds minus the natural welfare that we achieve and the natural welfare that we have by making suboptimal decisions. So in a very similar way, the regret is defined as before, but now instead of getting the sum of the different utilities, we get the natural welfare. And so we saw that a variation of a very famous algorithm in this setting called UCP achieves optimal regret with respect to the time horizon, with respect to the capital T variable. And in the following up work, some people achieved better regret with respect to the other parameters, such as the number of the slot machines and the number of agents in the system. So another very similar paper of Barman et al. Consider again the scenario where we have multiple agents, but now they consider a slightly different scenario that is inspired by clinical trials. So you can imagine that we have a bunch of different drugs that we can use for treating a particular remedy. And now we want to see which drug is better for a particular health concern. And so for doing that in clinical trials, usually in each time step, we have a different patient that arrives. And so and want somehow in this case to be fair with respect to all the patients, because somehow now the burden of exploration should be distributed among all the different agents. So it's not the same set of agents in each round, but in each round now we have a different agent. So you can imagine a different patient in which we allocate some remedy. And so again here, if we want to achieve some reasonable fairness, in each round we need to find a distribution over the different arms. So in this case, we don't have heterogeneous preferences. So in this case, there exists one remedy that is the best for all the patients. But the problem is how we're really going to find this fast, and also how we're going to allocate the burden of exploration. And so, as I said, in each round, again, we choose a distribution over the different remedies. And the reason is that if we just do this deterministically, then in some cases might be very unfair with respect to different patients. And so we want to choose a distribution. And in this case, again, the authors wanted to try to maximize the NAS social welfare. And so here they defined the regret as what is the optimal welfare, what is the optimal expected welfare that the agents could have, minus what we lose, minus what is the NAS social welfare of the expected welfare of the different agents. And so essentially here you can see that the regret is minimized as the NAS social welfare, which is the product of the expected utilities of the different ages, is maximized. So we want to maximize the NAS social welfare here, and so the regret is minimized in this case. And so again, the author saw that the variation of the same famous algorithm called UCB achieves optimal regret in this case, where you can see that here is not square root of t as it was before, but it is something much worse, but this is the best that we can achieve in this case. All right, so and with this, we concluded the part of how we can apply NAS social welfare to multi-embodied. So we saw two different settings. And now let's see a different application of NAS social welfare in classification. So in a recent work, the authors made the following observation about the standard notion of fairness that are usually applied in classification. So the standard notion of fairness are statistical parity, where essentially we ask that when we make a decision about a group, we don't get into account their sensitive attributes, but instead we want to be fair with respect to them without taking into account their gender or anything else. Or equalized odds indicates that we have the same ratio of true positive or true negative statistics over the different groups. So somehow we have some statistical fairness over the different groups that has to do with how these groups are partitioned according to their sensitive attributes, and we want to be to provide these statistical fairness guarantees. However, the observation that the authors had in this paper was that in some cases, statistical parity or equalized odds might return some solutions that do not seem so fair with respect to some group of individuals. And this unfairness in some cases is caused just because for some group of people, it is inherently very difficult to find a good classifier. So in particular, in their paper, they had this picture where they assume that there are two different groups of individuals, the individuals that are in the blue region and the individuals that are in the yellow region. And so what they noticed in their work is that independently of how we are going to choose a classifier for the blue group, there is no way to find a good classifier. So as long as, because you see that here, the positive or the negative individuals of the blue in the blue group. So you can imagine that positive means that they are classified as 1, and negative means that they are classified as 0. Because the positive and negative true labels of the individuals in the group, in the blue group, is very well blended, unless if we choose a very natural classifier, something very complicated, there is no a way to really classify this group of individuals in a good way. So if we choose, for example, just a linear classifier, then in any case, we will mess up with respect to this group, and we will not be able to achieve something better than what we do at random, for example. On the other hand, we see that this is not the case for the yellow group. we see that for the yellow group, if, for example, we choose the x-axis, in this case, we can have a very good classifier for them because most of the positive individuals are above the x-axis, while most of the negative individuals are below the x-axis. And so if we just use this classifier, then we're doing a quite good job with respect to them. But because under statistical parity or equalized odd, we want to be fair with respect to both groups, which means that if for some reason we mess up with the blue groups, then we should also mess up with the yellow group, because otherwise this solution is not going to be considered fair. We need, for example, to choose, in this case, a bad classifier for the yellow group as well, which might be the y-axis. So if in this particular example, we can choose between the x-axis and the y-axis, we are forced to pick the y-axis just because there is no way to classify the blue group in a nice way. And so after this observation, the authors pose the question that if there exists any way to treat every group of individuals in a way that they can be classified as good as they would be classified themselves. So if we ignore that there are other groups, and we had a perfect classifier for them, is there any way to provide such guarantee when there are other group of individuals as well? And so here notice that they ask this for any subset of individuals and not only for predefined groups, which is also something that statistical parity or equalized odds do not do. And so this is particularly important in practice because in some cases we might not have predefined group of individuals, we might not know the different groups of individuals, some of them might be hidden, not so obvious to detect. And so to try to define and provide some notion of fairness in each group of individuals can be particularly useful. And so for answering this question, in this work, the authors defined the following model. So first, they define the utility of an individual for a classifier as the utility to be equal to 1 if the classifier agrees with the true labor of the individual, which means that if a classifier given this individual outputs 0 and also the true label is 0, then the utility is equal to 1, otherwise 0 is equal to 0. And then they define the utility of a group as the average utility. So for any group, any subset of the individuals, they define the utility as the average utility of the individuals in this group, given a particular classifier F. And so given each group, they define the optimal classifier for a group as the one that maximizes the utility of this group, given a family of classifiers that from which we can choose a classifier. And so if there was no any other individual in an instance, and if we had just this group of individual S, that would be the optimal classifier with them. But now the question is that if there exists any way to return a classifier F for all the individuals, such that for each subset of the individuals, the utility that this classifier provides to these individuals is not much worse than the utility that they would get after the perfect classifier. And so they wanted to see what approximation we can achieve with respect to the classifier that we choose when there are multiple groups in an instance versus the classifier that we would pick if we had just this particular group. And they asked what this value of alpha can be in this case, or what the approximation can be. And the first observation was that if we just have deterministic classifiers, we cannot have any guarantee with respect to the best effort fairness as they define here. And the observation is very simple because we can see that when we have an imperfect classifier, so a classifier that in some cases makes some mistakes, and when we are in an instance where for each subset of individuals, there exists a perfect classifier, then in this case, unavoidably, we are going to be very unfair with respect to the subset of individuals that we misclassify, because while there exists a classifier for which they have utility 1, under the classifier that we choose, the utility is going to be equal to 0. And as long as we don't have a perfect classifier, we cannot avoid this, this to happen. And so that's why people consider randomized classifiers. So in this paper, the authors turn their attention into randomized classifier, which means that we return a distribution over the different classifier, over a family of different classifiers. And so the question was, what can we achieve when we consider distribution over different classifiers? And so first, they saw that there exists an instance in which there is no distribution, such that for every group of individuals for which there exists a perfect classifier, we can provide their utility for the distribution that we return is larger than the size of the group versus the size of the whole population. And so essentially here, we know that that there's no classifier or randomized classifier that even if this group of individuals have utility 1 for a particular classifier, which means that this classifier classifies this individually perfectly, then there's no way to return a distribution that provides a guarantee better than this. And so here we see that this depends on the size of the group as well, which is kind of expected because when the group is very small, we cannot really expect that to return a classifier that's perfect for them. And so after this observation, the question was, okay, we cannot hope for something better than this, but can we at least get a guarantee which is close to this? And so they noticed that if we try to find a distribution that maximizes the non-social welfare of the agents, which means that if we try to find a distribution that maximizes the product of the utilities of all the agents, then actually we can get this guarantee. So they actually saw that if we get the distribution that maximizes the non-social welfare, then for every group of individuals that admits a perfect classifier, we guarantee that their utility for the distribution that non-social welfare returns is at least equal to the size of the group over the size of the whole population. So somehow we achieve some proportional fairness with respect to them, because as the size of the group increases, then this guarantee is getting better. And also they saw that for every group of individuals, we can also have the guarantee that their utility of the distribution that we return is at least equal to the utility that they had before, square at the power of 2. And again, it depends on the size of the group and the size of the whole population. So we see that this guarantee is a bit weird because the parameter alpha that I defined before also depends on the utility that this group can get from the perfect classifier. And actually, the authors do not provide an example in which they saw that this is tight. So this is an interesting open question, I believe, to try to see if this is indeed the best that we can provide to all group of individuals. All right, so I think in the interest of time, I will skip the ranking section, or actually we'll talk about this very briefly. So rankings is also in the spectrum of recommendation system, but now the difference from the setting that Nisarg discussed before is that in each user, we saw a whole ranking over the different items that there are available, over the different products that there are available. And so in a recent work, people try to apply the natural welfare for getting fair rankings with respect to the products. And so in a very similar setting as the one we saw before, we defined for each item and for its agent, for its user and for its product, how relevant is this product to the user. And then when we are talking about rankings, we also get into account in which position of the ranking an item is exposed. So if it is exposed in a very, very low position in the ranking, then the probability of the user reaches ever this position is very low. While if we expose this product in in a high position in the ranking, then most probably the user will see this item. So there is a relationship between the position that an item is exposed and the probability of actually being noticed by the user. And so then they wanted to find a recommendation policy, which is that for each item Y, there exists a probability to be exposed at position K in the ranking of user X. And so then, by taking into account all these quantities, how relevant a product is for a user, in which position of the ranking this item is exposed to a user, and the probability of exposure, they define what is the utility of the different products for the different policies. And then they saw that if we find the policy that maximizes an social welfare, so again maximizes the product of the utilities of the different items, subject to natural constraints, that each item is advertised once at its user, and we have at most one item advertised in its position. And they saw that if we try to maximize social welfare, actually we achieve an approximation of envy freeness. So as we saw before, envy freeness is a quite desirable notion of fairness. And here we see that if we maximize the social welfare, we get an approximation of envy freeness in rankings. All right, and with this, we concluded the part of social welfare. Now let's move on to the last part of this tutorial, which is about the core. And so we discussed, so Nisarg in the introduction discussed two different notions of the core. One is related on utility scaling of the core, so of utility scaling, and the other was the resource scaling. So somehow we want to achieve proportional fair solutions that we get into account the utilities of the different agents, or what is the entitlement for a resource that we can allocate. So the plan was to talk for federated learning as well, but in the interest of time, I will skip this part. So, however, we will have this in the slides. If someone is interested to see how core has been applied in federated learning, they can later see our slides and see how it has been defined. And let's move on to the clustering setting. So as Nisarg mentioned before, in clustering, envy fairness has also been applied in clustering for achieving fairness. But now I will focus on the core, and I will describe how core can be defined in clustering, in centroid and non-centroid setting, and why it might be considered a better notion of fairness in this particular setting. Okay, so first of all, what is clustering and how we can think about this? So when we're talking about clustering in machine learning, the goal is to analyze a data set that we have. So you can imagine that we have different data points in a metric space, and we want to analyze the metric spaces in a way that objects that are similar are grouped in the same group. However, there are applications of clustering in economics as well, and these applications are known as facility location, where here the goal is that we want to build different facilities that serve different agents. So you can imagine that, again, we are somewhere in the metric space, and the different locations are different locations of different agents. You can imagine houses of different people, and then we want to decide where to build hospitals in a way that is fair with respect to all of them, and serve them in a good way. So first I will focus on centroid clustering. So in centroid clustering, we have as input a set of data points and a set of m-feasible cluster centers. So you can imagine that we can have a cluster center either everywhere in the metric space, and so then this set M is the whole metric space, or you can imagine that we have particular locations where we can have a cluster center or a facility, and it's not necessarily the whole metric space. And so here, all the data points and all the feasible cluster centers lie in a metric space. And under the assumption of metric space, we have some nice properties, and the most important is the triangle inequality, which means that the distance of a point I to a point J is not larger than the distance of a point I to L, and then distance of L to J. And this particular property is particularly useful. And now in a joint clustering setting, we want to select K centers, and then we allocate each data point to its closest cluster center. So that's the goal. Just pick K different centers, and then each data point is assigned to its closest cluster center. So in set-rate clustering, there are famous objectives that try to determine how we should pick these K different cluster centers. And so one famous objective is K median, which indicates that we should select the subset we should select K cluster centers in a way that the sum of the distances of the different agents to their closest cluster center is minimized. So by CI here, I just define the closest center to agent I, and K-median just try to minimize the sum of the distances. On the other hand, K-mean tries to minimize the sum of the square of the distances. And another very famous notion is a famous objective is K-center, which tries to find the K-cluster centers that minimizes the maximum distance in this case, and not the sum of the distances, but just the maximum over all the different agents. So I will return back on these famous objectives, and we will discuss why in some cases they might not be so fair. But before we do that, I would like to introduce how core can be defined in the clustering. So this idea was first mentioned by Chen et al. In a paper of 2019, where they made the observation that they wanted to find clustering solutions that are fair, where fairness is defined through proportionality, so through proportional entitlement. And the observation was that because we have n agents in total, and we want to create K different cluster centers, then every group of n over K agents deserves to choose its own cluster center. So under proportionality, because we have n people in total and K different cluster centers, every n over K of them are eligible to select their own cluster center. And so under this intuition, they used the idea of the core that defined from economics for defining what is fairness in clustering. So just to show you just to make a connection with how core is defined with committee selection, I remind you that as Nisark mentioned before, in committee selection, we're saying that the committee is in the core if for any subset of individuals and for any different committee, if this subset of individuals is large enough and can support this subset of committee, then it should not be the case that all of them Pareto improve by deviating and choosing this particular committee. And so the idea in committee selection is that if a group can afford a different committee capital T, then this committee should not be a Pareto improvement for all of them. So in a very under a very similar flavor, we can define core in clustering, where we're saying here that a clustering solution C is in the core if for any subset of individuals and any feasible cluster center, if this subset is large enough, then this new cluster center should not be a Pareto improvement for all of them. So under the similar flavor, if a group can afford a different feasible cluster center, then this cluster center should not be closer to all of them rather than their closer center in the original solution. So this is how the resource allocation version of the core is defined in clustering. And just to show you this through an example to make it a little bit clearer, imagine that we have 6 different individuals, which are denoted by these blue balls. And imagine that we have 4 different feasible cluster centers, which are denoted by these black boxes. And imagine that we want to create two cluster centers. So if we assume that we select these two cluster centers, then we see that all the individuals on the left, 1, 2, and 3, actually prefer, for example, cluster center C, cluster center 2. And if all of them deviate to this cluster center, then all of them decrease their distance to their closest cluster center. And because we have 6 individuals in total and we want to create two cluster centers, this means that under proportionality, every 3 of them are eligible to select their own cluster center, which means that these 3 are eligible and can support to get as a cluster center, the cluster center 2. And so the initial solution was not in the core. So now if we consider this solution, we can see this is in the core, because even if there are some people that might prefer a different cluster center, for example, 1 and 2 still prefer cluster center 1 versus cluster center 2 because it is closer to both of them, their group is not big enough for supporting to get their own cluster center, and the same it is for agents 4 and 5. And so this solution that we have here is in the core because there is no a group that is sufficiently large and prefers a cluster center that is not in the solution, in the current solution. Okay, so Zenithal saw in general that the clustering solution is in the core does not always exist. And so that's why actually they defined an approximation of it. And they ask if there exists a solution that is in the alpha core for some parameter alpha, where essentially this parameter alpha indicates how much a group of individuals or a group of agents can improve their distance if they deviate to a different solution. So the larger the alpha is, the larger the larger violation of the core we have. So the question is if there exists a small enough alpha that provides a small enough alpha for any group of individuals. So if we can have a guarantee for a small alpha. All right, and so Zenithal saw, first of all, that indeed there exists an algorithm that provides a reasonable small constant, so a guarantee that depends on a small constant. And they actually saw that there exists an algorithm called greedy capture that returns a clustering solution in the 1 plus square root of 2 core under any metric space, which means that even if there exists a group of individuals that can deviate and can choose a better solution for themselves, then the improvement that they experience is not larger than 1 plus square root of 2. So how much they improve is not a significant quantity. And they also saw, they asked how tight this is for the best that we can do, and they saw that for any metric space, there are instances in which we cannot provide a guarantee better than 2. So essentially, there are some instances of the best that we can show is that all of them can improve by, that there exists always a group of individuals that can improve by a factor at least equal to 2, and so we cannot hope to get something better than 2. However, here you see that still there exists a gap between 1 plus square root of 2 and 2. So probably it is an interesting question to try to close this gap. We don't know which direction to go, but this is an interesting open question. Now, in the following up work with NISARC, we saw that actually greedy capture provides better guarantees when we consider delta norm, so when we are in the Euclidean space. So in particular, we saw that when for each data point the distance is defined according to delta norm, then greedy capture actually returns a clustering solution in the 2 core. And so we see that we have a better approximation than before, which was the general 1 plus square root of 2 for any metric space. So that was quite surprising for us. And so we asked if this is the case for other famous metric spaces as well, such as when we use L1 norm or when we use L-infinity norm. But it turned out that this is not the case, that actually there are some instances where greedy capture indeed does not provide any guarantee better than 1 1 plus square root of 2 for these particular metric spaces. So even if we are able to get a better guarantee for the Euclidean space, this is not the case for other metric spaces. And then we asked for lower bounds for this particular metric space as well. And we saw that under the Euclidean metric space, we cannot get a guarantee better than 1.15, roughly 1.15. But still, we see that there exists a gap here. We were not able to close it. It might be an interesting equation. And same for L1 and L infinity, where we saw that the clustering solution in the alpha core for alpha less than 1.4 is not always guaranteed to exist. So again, there is a gap here with respect to the greedy capture, and these are interesting questions. So of course, now let's go back to the classic objectives, because someone can water and can say, why do we want the core? Why don't we just try to apply k-means or k-medians, and what is wrong with them? They're not fair. So in this picture, I want to show you that in some cases, k-means and all the classic objectives, first, are very sensitive to outliers. And second, they might not be very fair under the idea of proportionality and entitlement. So considering this particular case, where we have almost half of the individuals to be in one position, let's say this left top position here, and the remaining almost half individuals are again in another position, which is this bottom left position here. So these two cohesive groups are quite close together to each other, but again, they're not very, very close. So they are two well-distinct group of individuals. But also we have two other individuals that are very far away from anyone else. And we can perceive this as two outliers. So if we try to apply either k-means or k-medians or k-center, all the classical objectives, the solution that would return is that they will classify the two cohesive groups together because they are close together to each other. And then they will use the other two cluster centers for classifying the two outliers. And so essentially the waste two of the cluster centers that we can have for just serving the two different outliers. But here we see that while half of the population is in one position and under entitlement, they deserve to have their own cluster center, they should share their own cluster center with the other half of the population just because they happen to be relatively closer than the other two outliers are. So this doesn't seem very proportionally fair, but the fair solution would be the one where we use the two cluster centers for serving the two distinct groups that are very cohesive, and but they are again quite distinct from each other, and then using the last cluster center for serving the two outliers and capturing the two outliers. Okay, so this is a high-level idea, while in some cases core might be a good notion of fairness in clustering versus classical objectives. And now in the last minutes, I would also like to discuss how the core can also be applied in a non-centroid clustering setting. So as you saw before, the non-centroid is very similar to the centroid case, where again, we have as input a set of individuals, where all these individuals lie in a metric space. But here, there are no feasible cluster centers, and the goal is not to create cluster centers, but instead, the goal is to partition then individuals in the input into K clusters. And so here, each individual does not care for the distance to the closer cluster center because there are no cluster centers, but instead each individual cares about their loss for the group that they belong. And so the loss of an individual for the group that C belongs can be either their maximal distance to any other individual or their minimum distance, or the sum of the distances and the average distances and so on. So I keep this for now quite abstract, and I will mention in a while more specific loss functions. And so we defined in a recent work alpha core in a very similar way here. So again, an approximation because a solution in the core does not always guarantee to exist. And so here we said that, it's a group of individuals that it has size at least n over k is eligible to deviate to their own clusters, to their own group, to their own cluster, if all of them apparent to improve in the sense that they have lower loss for the new deviating coalition, for the new group that they create, versus the loss that they had for the group that they were belonging under the clustering solution. So here CI is the set of individuals that belong to at the same cluster as individual I. So just we just applied the core in a very similar flavor. And then we focused on the average loss. So we assume that the loss of individual for a group S is equal to the average distance that she has to an individual in the group. And we asked what kind of guarantees we can get in this case. So first we saw that greedy capture returns a clustering solution in the 1/k core under any metric space. So you see that as k grows, this is quite small, but when k is small, this is quite large. So this is not a perfect approximation. And the question so though is this indeed the best that we can achieve? So we were able to show a lower bound that is constant. So it was quite non-trivial in this case to show than the Cedroid setting to show that a solution in the core does not exist to actually have this non-approximability. And so we saw that for our arbitrary metric spaces, we cannot have a clustering solution in the alpha core for alpha less than 1.366. So you see that there exists a huge gap here. So it is a constant versus n/k. So there exists the open question whether in this case we can have a clustering solution that is in the core for some constant. And I think it is interesting that Nisark and I disagree with respect to this question. For example, I believe that the correct answer is that there exists a constant, while Nisark does not believe that. So I think it would be very interesting to see what is the correct answer. So again, why correct versus classical objectives in this setting? We have exactly the same image as before. And so again, you can see that the classical objectives would group the people in this way, would have these two outliers in a group by themselves, and then one big group for all the remaining individuals. While if we apply the core, we get something that seems fairer. And now also, as you saw before, in non-Cedroid clustering, people have used NB freeness as a notion of fairness. So a reasonable question is why core and not NB freeness? So of course, in some cases, NB freeness might make a lot of sense, it might be fair, but in this example, we see that again doesn't capture the idea that cohesive groups should be on their own groups, that similar individuals should be clustered together. And to see that, imagine that we have this instance where we have two individuals that are very close to each other and two other individuals that are far away from anyone else. And then if we want to create two groups of individuals, two clusters, then what seems reasonable under core and under the intuition that similar individuals should be in the same group is to cluster the two people in the center, the two people that are very close to each other together, and then cluster the other two people that are far away from anyone else together. But actually, under NB freeness, what we are forced to do to achieve NB freeness is that we need to cluster then two individuals along with another individual that is quite far away from them, and then to cluster the individual that's further away from anyone else by itself. So essentially, the cohesive group in the center, while they deserve to have their own cluster, they are forced to cluster together with an individual that is an outlier for them. So NB freeness in some cases might not be a very reasonable notion of fairness in this setting. All right, and with this, we concluded the core part as well. So here you can see a list of the references and the papers that we discussed today, along with some other papers that we didn't have the chance to discuss, but are in the same context. So if you feel that some paper that is important is missed from this list, please feel free to reach out and we are happy to expand the list. And let me stop here and probably we can use a few minutes to have for any questions. Thank you so much.